Hello everyone, welcome to Enzo Science. Today I'm going to be talking about the amazing book by Diesenroth, Feazell, and ONG, Mathematics for Machine Learning. I just finished reading this 2 weeks ago, and I've also finished my exams, and as promised in the last video, I'm going to talk about this now. Isn't that exciting? Without further ado, let us begin. The book, Mathematics for Machine Learning, much like this video, is sort of separated into two parts. The first being about the actual fundamental math behind machine learning, or as they say, mathematical foundations. And the second part of the book being about how these foundations are applied to real machine learning in the form of linear regression and other things. So then we have central machine learning problems. And the central machine learning problems go from just basic graph models to linear regression to gradient descent by not gradient descent, machine learning via Gaussian mixture models. These are basically, those are really cool. I'll get to that later. I almost got ahead of myself there. But let's start with the mathematical foundations. The mathematical foundations of machine learning are really mostly linear algebra with a lot of vector calculus and what is the other thing called? Analytic geometry, that's the other thing. And the reason it's mostly linear algebra, as I've explored in my previous videos, it's really a neural network, or a lot of machine learning is neural networks, is just one matrix being multiplied by another matrix and then being added to a scalar, the bias. Because of this, it's all linear algebra, but the other parts of it come in when you're looking at specifically training those networks. Like when you're training a neural network, you have to find a gradient of a slope. You got the slope, and then you have to find the gradient of the line, and then you can move down it. And this requires calculus, of course, that you're finding a derivative of that line. Yeah. The second portion of the book, the one on problems of machine learning, which I showed you earlier, is really focusing on the basic concepts that machine learning use but are still a high level from the linear algebra and actual mathematical building blocks. These are linear regression, Gaussian mixture models, as well as dimensionality reduction, and I forgot what the other one was called. Let me look it up. Oh, regression. So regression is, can this move faster? Come on. Or regression, or linear regression, is more or less you can think of it as making a function to fit some data set. So you have like a graph, right? You have points of data on it, and then regression is a little line that goes through all that data. And then it tweaks where the line is, and using activation functions it can bend that line. Regression. Yeah. And then you can also determine the distance between the line and then like the points to determine how bad or good it's doing, etc., etc., etc. Dimensionality reduction is actually really interesting, in which case you can essentially use some fancy math in order to approximate data. Let's just say you wanted to approximate the MNIST dataset. That's the 28 by 28 pixel images. There's a great illustration in here I want to show you. It'll be a minute for me to find this. So here you can see the original MNIST images at the top, and then basically varying levels of approximation. As the amount, let me focus over in this general direction. This camera on this computer kind of sucks, but just take my word for it that as the amount of approximation increases, the closer it gets, but it's still less. So that way the model can handle more data as a whole. It makes the entire system more efficient. Then there's Gaussian mixture models. Let's just say you have a data set, another coordinate plane, with two groupings of data that are not really next to each other, so you couldn't apply one Gaussian to all of it without it being like really non-representative of what you're actually trying to look for. So you can add like two Gaussians, one larger, one smaller, whatever, and sort of mix them, hence Gaussian mixture model. And let's just scroll through here, see if I missed anything. And then, of course, they use classification using an SVM, or support vector machine, which is a very interesting method. And that can be used a lot, mostly for classification tasks. The other central theme, besides linear algebra and calculus, in the mathematical foundations of the book is probability and distribution, which really goes into how like if you're going to randomly guess something would happen, what is the probability of that? And then using weights, how can you maximize that probability is sort of what it's leading towards, and it heavily influences the rest of the book, including bringing up things like Bernoulli distributions, Gaussian, mixed Gaussian, what are they called? Gaussians, just in general, as well as Bayesian inference stuff as well. Very useful for machine learning outside of the linear algebra scape.